Okay, so we're gonna get started on section 2.3, and we're gonna look at the application of the exponential function in this section. All right, so we're using the exponential function to model the population growth in this section. And population growth is a phenomenon which is compounded continuously. Meaning population is increasing continuously. I'm going to show you some real world data so you can appreciate what we mean by increasing continuously. All right, so we're going to focus on solving a real world problem. In this case, real world application problem is population growth using the property of exponents and exponential function. Okay, so why do we study exponential function? Because exponential function are used widely in the real world measure growth, interest, and then decade. So population growth is one of the important topics. And also compound interest, that's another important term in finance. Growth based exponential function, meaning we get an exponential growth model. An exponential growth model could be used to capture the growth of rumors, human population, bacteria, computer technology, nuclear chain reaction, and compound interest. And we're going to focus on exponential growth model in this section. We also have exponential decay model, meaning it's decreasing at a constant rate, a certain rate, right? So that's what we call the exponential decay model. But we won't go into this area at all, right, in this section. But just remember, exponential decay model could be utilized to capture the half-life of the nuclear element, Newton's law of cooling is using the exponential decay model. And a lot of real-world applications involved with that. Now I'm going to show you some real-world data about population growth. Okay, so you go to Google and type in world population real time. And you're gonna have this website pop up, and as you can see, this clock gives us the. You can click on the first icon here, first web link, and then you're gonna see the current world population retrieving now. If you pay attention to this population, as you can see, this current world population is increasing continuously every second, right? If you look at it, it just keep going up. So using the natural exponential function, we can actually capture the growth of the world population. Okay, so that's where the this exponential model comes from, and there are a lot of websites giving us the real-time, world population, and we can. Let's get into the detailed calculation in a second. Right. So first of all, let's look at the model first. So the model we are using here is the foreign model, population growth model. So you get NT equal to N0 times e to the KT. So this is the model we are using here. In this model, first thing is NT. NT is the population at a time t, or you can say after t years. So you can also say that that's population in the future, and N0 represents the initial population. So that's where the at the very beginning, what is the population? Well, that's N0. And then K here represents annual constant growth rate. So for every county or every state, city, and then entire country or the entire world, we can always come up with the annual constant growth rate, and then U.S. Census actually post those data about the annual constant growth rate. That's why every U.S. citizen participated in the U.S. Census. So they gather data and publish all those data for the public use. And then here time, T is represent time in years, and then the unit for T must be years. Cannot be month, cannot be days, it has to be years. And here E is what we call a natural number. And E is approximately equal to 2.718. Natural exponential function is used to capture the continuous compounding phenomenon. Okay. So that's why this model, the base here is E, right? Base is E. And E captures continuous compounding nature. Right. Now let's look into some examples and then try to utilize the formula to analyze the situation. First of all, a population of 1,200,000 grows with the annual growth rate of 1.25%. What is population after 5 years? So once you have the real world problems like this, you analyze the information given and then figure out which variable fits each number. In this case, we are looking for the population after 5 years, so we are looking for NT here. NT is unknown, right? So we're looking for that. Now what's given here is 1.2 million. This is what we call N0, initial population. Okay, so 1,200,000. We also given the annual growth rate, K, that's 1.25%. And then we also know time T, that's 5 years. So it's after 5 years. Now in the formula we have actually 4 variables. If you know any 3 variables, we'll be able to solve for the missing one. So here NT equal to N0 times E to the KT. And all we have to do is plug in all the numbers into the formula. N0, that's 1.2 million, 1,200,000 multiplied by E. K is 1.25%. You can turn it into a decimal, or you can keep it as percentage. It doesn't matter. Okay. And again, we have to use a calculator or Excel to do this. So I'll show you how to get this number right now in Excel. And calculator have a similar input, right? So you're gonna put in equal sign first, 1,200,000 multiplied by EXP, represent E to certain power, 1.25% multiplied by 5. Okay. And that will give us the number, and that gives us 1,277,393. And that's the population after 5 years. So this is 1,277,000 and then 390. That means the population after 5 years is 1,277,393. Okay. So analyze the situation, assign a variable, given numbers, and then we solve for the unknown. All right. Second example, a population which is 295,000 now has a constant growth rate of 1.35% over the last 25 years. Last 25 years. Okay. A constant growth rate is given. So K is given 1.35%. Time T is given last 25 times equal to 25 years. What was the population 25 years ago? And this compare the population now, 25 years ago, this should be the initial population, N0. So N0 is unknown. We're solving for N0. Then NT must be the population right now, which is 295,000. We know NT, we know K, we know T. We are solving for N0. So right here, we're just gonna do this. All right. So NT, apply the formula NT equal N0 times e to the KT. Now we just plug in all the given numbers. NT is 295,000. E, K is 1.35%, times time t, that's 25. And we are actually trying to solve for N0. So all you have to do is get N0 by itself. So we're going to divide it E raised to 1.35% times 25 on both sides of the equation. E 1.35%. We're going to cancel this exponent, and the N0 is by itself. So the N0 is equal to 295,000 over E raised to 1.35% times 25. And again, we put into the calculator or Excel to get the result. All right, so we're going to go to the Excel right now and type it in. So we get 295,000 divided by EXP, E raised to a certain power. So it's 1.35% multiplied by 25 years. Okay. And that should give us the initial population here. And the initial population turned out to be 210,000 and then 498. 210,000 and then 498. So initial population 210,000, 498. Okay. So that is how we find out the initial population in this case. So every problem may be different. Even though you look into the real world problem, it could be different, right? You look at different counties or different city or different state, they all look different. So third example, according to the US Census collect data about the entire population in the United States. So the population of the US was 248.7 million in 1990s. In 2000, it had grown to 281.4 million. What was the annual growth rate for the US for this period? So now, definitely we're looking for K, right? Annual growth rate, that's what we're looking for. And let's see. In 1990, we treated as the initial population. So the N0 equal to 248.7 million. Now we want to expand it as a standard form. It's okay. We can, because the unit are the same for the initial population and then ending population. So we're okay. So and then in 2000, the population has grown to 281.4 million. So NT here equal to 281.4 million. And then from here, we also know the time t because between 2000 and 1990, now 10 years. So 10 equal 10 years. So one more time, we know three numbers in the formula. We can solve for the k. Okay. So NT equal to N0 times e to the kt, and we're solving for k here. So NT, that's 281.4 million. Equal 248.7 million times E, K unknown, but the time t we know, so it's K times 10. All right. And as you can see, since they have the same unit on both sides of the equation, so that's why we didn't expand it. Same unit, when you're dividing 248.7 million from both sides of the equation, we'll be able to cancel the millions, the unit. So this constant get cancelled, the million get cancelled, end up with that. And then let's switch the order. We get E 10k, 10 times k equal to 281.4 over 248.7. So in order to solve for this, solve for k, we have to take in the ln from both sides of the equation. So we take in the ln on the left, we get E and k. And we take in ln on the right, we get 281.4. Taking the logarithm base E. Okay. So ln and E, they offset each other, so end up with 10k equal to ln of 281.4 over 248.7. And then after that, we divided 10 from both sides of the equation, we get a k. So k is by itself, and let's see what the k is. Again, we gotta use the Excel calculator. So I'm gonna use Excel. So here we do ln, we equal sign first, ln, and we put in the 281.4 over 248.7 and dividing by 10, and that will give us the rate, the constant growth rate. And this turned out to be, usually we turn into full decimal place. Okay, so for the rate, run to full decimal place. Okay, that's a convention. Okay, so it's 0.0124. So let's go back, 0.0124. 0.0124, and if you turn it percentage, it will become 1.24%. Move the decimal to the right 2 units, insert a percent sign. Right, so it's 1.24% growth rate within these 10 years. And example 4, the world population is estimated to be growing at 1.33% per year. So constant growth rate k is even. The population is about 7.9 billion right now. How long does it take to reach 10 billion? So 10 billion, that's within the near future. 7.9 billion is right now. Right? So n0 equals 7.9 billion. Again, they have the same unit. So we're gonna keep the unit there. And the NT is given. In the near future, the population will reach 10 billion. And the only thing we don't know is how long, time t. So we're looking for time t. So now very similar procedures compared to the previous one. We're gonna find all these numbers. So nt 0, throwing on the numbers here, 10 billion goes to the left. Nt n0 is 7.9 billion times e. K, we know it's 1.33%. And time t is the only unknown. So we're solving for time t here. So step number 1, we're dividing 7.9 billion from both sides of the equation. And as you can see, since they have the same unit, they offset each other. If the two quantities are not given in the same unit, then you have to expand it in the standard form. But in this case, they are. Okay. So cancel this unit, cancel the number on the right. Reverse order, we get E 1.33%. And that is equal to 10 over 7.9. So similarly, very similar procedure from the previous one. We're taking the ln from both sides of the equation, 1.33%. So based on the inverse property, logarithm base E, exponential base E, they offset each other. ln of 10 over 7.9. Okay. So this whole thing gets cancelled. We end up with 1.33% on the left, and ln of 10 over 7.9 on the right. Now the very last thing, you want to turn the 1.33% as a decimal number, 0.0133. That's okay. Ln of 10 over 7.9 dividing 0.0133 from both sides of the equation. Cancel that. T is by itself. Let's see how many years that is. Okay, so again, we're putting to the Excel. Ln of 10 by 7.9 and dividing by 1.33%, which is 0.0133. Okay, that should give us the time t. And typically we run it to one decimal, so 17.7 years. That's how long it takes. So for time t, run it to one decimal place. Okay, so 17.7, that's the answer we're looking for. 17.7 years. Okay, so this is solving for time t. So basically, we're looking at each one of this scenario and then solve for different variable here. Example 5, India's annual growth rate is 4.8%. Right? At this growth rate, how long does it take the population to double? Right. So this is what we call the doubling problem, because they're talking about doubling the population. Doubling time. Yeah. And again, how long? That's time t, right? So it's solving for time t. And we know the growth rate that's given. So k is 4.8%. You want to take the decimal is 0.048. And we don't know n0 and nt, right? So we can assume n0 is 1 unit. It's not 1 people, right? It's 1 unit. 1 unit could be 1 billion or maybe 1 million, something like that. And then nt will become, because doubling, so it's 2 units. All right, so this is 1 unit and 2 units. This is exactly the notion of the doubling. Now, again, we're solving for time t, right? So we're applying all this into the formula. So nt equal to n0 times e to the kt. And now right here, 2 units to go to the left, and 1 times e. K is 0.048 times t. So very similar procedure. We're going to solve for time t. So omega 1 e 0.048 times t equals 2. Now you're taking ln from both sides of the equation, so ln of e 0.048 t ln of 2. Then we offset ln and e, we end up with 0.048 t equals ln of 2. Dividing both sides of the equation by 0.048. Cancel that time t by itself. So it's ln of 2 by 0.048. Alright, so it turned out to be 14.4 years. So 14.4 years, that's what it takes for India to double the population. 14.4 years. And this is a very typical doubling time problem. Okay. Now let's take a look at another example here. Population is 1.32 million in 1983 and then 1.45 million in 1995. What is the tripling time? So, problem here has 2 elements, right? We're looking for tripling time. However, we only given the first duration is initial population is 1.32 million in 1983, 1.45 million in 1995. So here for the first condition, n0 equal to 1.32 million. And then nt is equal to 1.45 million. Since they have the same unit, if you don't want to keep the million, that's okay. And then time t is equal to 1995 minus 1983. That's 12 years. So now, based on this, we can solve for k, right? So this is important. We gotta solve for k first. K is unknown, right? Once we know the k constant growth rate, then we can find out the tripling time. Now, first step is let's solve for k. So nt, that's 1.45 million. I will skip the unit and nt equal to n0 times e to the kt. N0, that's 1.32 million. Skip the million because we're going to cancel that in a second. E and k times 12. All right, then we first of all dividing 1.32 from both sides of the equation. So e to the 12k equal to 1.45 over 1.32. Now similarly, we're taking the ln from both sides of the equation. Ln of e of k equal to ln of 1.45 over 1.32. Cancel that 12k equal to ln of 1.45 over 1.32. Here we're dividing 12 from both sides of the equation, we get a k. And the important thing is here, since k is not a final result yet, so we're going to keep as many decimals as possible to make sure it's accurate when we figure out the tripling time. So this is important. Keep that in mind. Keep as many decimals as possible. Right, so we're going to do this. ln of equal to ln of 1.45 divided by 1.32 and divide by time t at 12 years. Okay, so we get a k. So it's 0.0078. Double check number one more time. Yeah, that's good. Oh, 12, that's good. Perfect. So go back to the Excel and we're gonna run it to 4 decimal place. 0.0078. Okay, so this is 0.0078, and we're gonna turn into a percent. Point. No, actually, more decimal is better. So maybe a couple more. 0.0078277. 2765. 0.00782765. So the k is 0.0078 2675 time 2765. So the more decimal we keep, the more accurate for the tripling time we end up with. So now let's look at the tripling time. Second step, the tripling time. So now k is given. 0.00782765. And n0, since tripling, assuming n0 is 1 unit, then nt will be 3 units. Okay, that's how the population triples. Here, the only thing we don't know is time t, so we solve for time t. So nt equal to n0 times e to the kt. Here we're solving for time t. nt is 3 unit, n0 1 unit times e. K we know 0.00782765 times time t. All right. Now reverse order e 0.00782765 times t equal to 3. And we're taking ln from both sides of the equation. Then we end up with 0.00782765 times t equal to ln of 3. And divide both sides of the equation by the decimal number. So the time t is equal to ln of 3 over 0.00782765. Now, one more time, get a result from the Excel. So it's going to be ln of 3 divided by 0.00782765. So we get that. So it's about 140.4 years. So it takes about 140.4 years to triple the population based on this constant growth rate. So time t is approximately equal to 140.4 years. Okay. So this is a typical tripling time problem. Now the last question we have here is, how long will it take a population with a growth rate constant of 2.7% to increase by 80%? All right, so the case given, we got that, is 2.7%. That's given. And we know the relationship between the initial population and ending population, right? So assuming N0 is equal to 1 unit. Now increase by 80%, meaning NT is equal to 1 unit plus additional 80% of 1. Okay. Increase by 80% based on the original base. Original base is 1 unit. So we end up with 1 plus 80 is 0.8 times 1, that's so it's 1.8 unit. So the initial population is 1 unit. The population, ending population is 1.8 unit. And we are solving for time t, how long? So time t, we are looking for that. So now similarly, we apply the formula nt equal to n0 times e to the kt. Now plugging all given numbers, nt is 1.8, n0 is 1, e, k that's 2.7%, and time t that's what we're looking for. Now e raised to 2.7% times t equal to 1.8. And we take in ln from both sides of the equation. One more time. And then that's equal to ln of 1.8. And then simplify a little bit, so we get 2.7% times t equal to ln of 1.8. And we're going to solve for time t by dividing 2.7% from both sides of the equation. So we cancel that, time t is by itself, so end up with ln of 1.8 by 2.7%. So one more time, you either use a calculator or Excel to do this. This is equal to ln of 8 by 2.7%. So you're going to put in 2.7% directly, that's okay. Even your calculator, you can do the same thing. Get a result. So it's 21.8 years. We run it to 1 decimal place. So it's 21.8 years. 21.8 years. That's the final answer. Again, this section just mainly uses one formula, so that's the population growth model, exponential growth model formula, so we can look into the details, analyze the situation, and solve for the unknown, right? So that's all you have to do in this section.